Welcome to this lecture series in group theory. Today we'll be looking at another very important group from the point of view of number theoretic applications. Last time we discussed the group Z mod nz, which was defined as follows. So fix some integer n greater than or equal to 2. It is not really necessary to do this, but just for the sake of concreteness, let us fix it. Otherwise, I have to say a little bit more, and there is you'll in no time be comfortable with negative integers with the same thing. So right now, for now, just n positive and greater than or equal to 2. So for any integer a, we defined a bar as this set. Basically, all those integers which are of the form that all those integers b which are of the form that b minus a is divisible by n. So that's what this set is. Okay, and then Z mod nz was defined as this way. Maybe I said something a little bit different, but it is equivalent to saying this, and that we observed, or we can observe right now, that this thing is actually equal to that. So take this as a little exercise if you don't immediately see it. And then we defined an operation on Z mod nz which sent a bar comma b bar to this set. Basically, you can choose a representative of an element here and an element here, and then just get the corresponding element in Z mod nz. And this is well defined for the reason because we actually didn't define it this way exactly. What we did was something else. We said that it is a bar plus b bar, which I don't want to get into, but if you followed the last lecture, this shouldn't bother you. And lastly, lastly, I want to comment that the size of this guy is n. We didn't explicitly perhaps say it, but it is clear from this observation. All right, so this is one group that will be important from the point of view of number theory. Today we'll be looking at a cousin of it, which is much more interesting than this group and much more has richer structure. Okay, so again, fix some two non-empty subsets of Z. These are non-empty subsets. I don't want to write it, but yeah, just they are non-empty. And we define their product. I put a dot here. Their product as, one can guess, x, y. So this is the usual multiplication of x and y, where x is chosen from A and y is chosen from B. Alright, so this is just some definition very analogous to what we did for addition. Last time we had defined something like this. Today we are defining something with multiplication. Alright, and then this we have a corresponding lemma also. Last time we had that a bar plus b bar is a plus b bar. Today we have a very similar thing, except for addition we have multiplication. So I leave this as an exercise because the proof is exactly similar to what we did the last time. So this is an exercise. And now we can hope to define a binary operation on Z mod nz, another binary operation I should say. We have already defined one the last time. So this time the binary operation will make use of the multiplicative structure that we just discussed. So what we'll do is we'll take a bar and b bar. Let me use a different color. We'll take a bar comma b bar and send it to a bar dot b bar, which we just saw is equal to a b bar. Okay. So question is this a group? So associativity, that you can easily check. So that is an exercise. Identity. 1 bar dot a bar equals, well, 1 times a bar, which is a bar, which is a times 1 bar, which is a bar dot 1 bar. So 1 bar does indeed act as identity. So this binary operation indeed possesses an identity. Inverse, well, 0 bar does not have an inverse, because 0 bar times a bar is equal to actually 0 bar, which cannot be equal to 1 bar. Right, because n is greater than or equal to 2, this cannot be equal to 1 bar. So the identity does not exist. Inverses don't necessarily exist under this binary operation, and hence we conclude that this under the dot defined above is not a group. But we can make it into a group or rather we can still extract an interesting group out of it. And that is the subject of this lecture. So just one second. Yeah. So we define Z mod NZ star as those things in Z mod NZ such that there exists some element, let me just say some elements in Z mod NZ, so that with the property that, or let me just say such that A bar B bar is 1 bar. So we collect only those elements which have an inverse, right? So fine, that is a set. And we would now like to think that this is a group. So first of all, does this binary operation restrict to that set? What does that mean? So clearly this thing is a subset of Z mod NZ. So this maps inside Z mod NZ a priori. This is the dot map that we defined above. Okay. So if we can show that actually the image of any pair here lands inside Z mod NZ star, then at the very least we have a binary operation on it. But does it? So if A bar in Z mod NZ star, or let me say we pick a pair A bar comma B bar from Z mod NZ star cross Z mod NZ star. Then want to show that this is also in Z mod NZ star. Right, so how do we do this? Well, I could leave this as an exercise, but here's the thing. Since A bar is in Z mod NZ star, there is some A prime such that A bar A prime bar is equal to 1 bar, and there is some B prime such that B bar B prime bar equals to 1 bar, and A bar A prime bar equals to 1, this is same as saying that A prime bar equals to 1 bar, and which is also equal to B prime bar. And now just observe that AB bar times A prime B prime bar is equal to 1 bar. So why is that? Basically just multiply this with that would be equal to this multiplied with that, and hence this multiplied with that is equal to 1 bar. But this multiplied with that is equal to this guy, and well, y is equal to this guy because A prime bar times B prime bar equals A prime B prime bar, which is equal to 1 bar as we just discussed. So yes, indeed, if A bar and B bar are in Z mod NZ star, then AB bar is also in Z mod NZ star. So this actually is legitimate to write. I can write this. So the image of this guy is contained here. So we have a binary operation on Z mod NZ star, and associativity follows because associativity held for the larger object. Identity still will follow because it was there in the larger object. So yeah, so 1 bar lies here. 1 bar is an element of Z mod NZ star because 1 bar times 1 bar is 1 bar, right? So if you take A as 1, then B as 1 serves the purpose. So 1 bar lies here, and hence identity exists in this guy. And inverses exist by force. That is how this was constructed. So maybe the only thing here to check is that if you have A bar in Z mod NZ star, so that you do have a B bar with a bar b bar equals to 1 bar, one just has to check that b bar is also in Z mod n Z star, but that's clear because you can just write it in the reverse way. Then you can just say b bar a bar equals to 1 bar, and hence b bar is also Z mod n Z star. So everything has an inverse. So the upshot is that Z mod and Z star is a group. And let me try something new, this which I found very recently. Yeah, so let me let me be fancy and use this. So the upshot is that Z mod and Z star is a group under this binary operation, under dot. Let me also write that under the binary operation dot just discussed. So very nice group. And we would like to get some handle on what the elements here look like, and that is the subject of the next lemma. So here is what we want to say. Z mod and Z star is just, you pick those integers which are relatively prime with n and take the remainder class and put all of them in a box or a set as you will, and that is Z mod and Z star. So here is the proof. Okay, so which side we should do first? Let's first do this containment. So let a be relatively prime with n. Want to show that a bar is in Z mod n Z star. So we will use Euclid's theorem. By Euclid, there exist x and y integers such that ax plus b, not b, ax plus ny equals 1, and therefore a bar x bar plus n bar y bar equals 1 bar. So how did we write this? Let me break this down. So what we get is that this is equal to that. That much is clear, because if two things are equal, the corresponding remainder classes must also be equal. Therefore, because that's how sums behave, we saw this. So we can write that. And this is how products behave. So we can write this. Here there is a dot which we are not writing, we are just suppressing the dot. Generally we do suppress dots. So we have that, and now n bar is 0 bar, and 0 bar times y bar is again 0 bar. And if you add 0 bar to anything, you get the same thing. So we get a bar x bar equals 1 bar. And therefore a bar is in Z mod n Z star. And what we have shown, we have shown the containment that this guy is contained in Z mod n Z star. The reverse is very, very similar. So let a bar in Z mod n Z star for some integer a. Then by definition, there exists some integer b such that a bar b bar equals 1 bar, which means a b bar equals 1 bar, which means a b minus 1 is divisible by n. So n divides a b minus 1, which implies a b minus 1 equals n times some integer, let's call it q, for some integer q, which implies a b minus nq equals 1. And if d were the GCD of a and n, then d divides the left hand side, and hence d also divides the right hand side, and therefore d equals 1. So the GCD of, let me draw an arrow here. So this implies GCD of a and n equals 1. And this work shows the reverse containment. This shows that Z mod n Z star is contained in those, the thing on the right hand side. Why am I even writing this? So these two containments show that this is indeed equal. So we have that. And lastly, horrible. Lastly, another. I'll just improve upon the previous lemma. So I want to say that Z mod and Z star is a bar with this constraint GCD a comma n equals 1. So this is not very different from the previous lemma. In the previous lemma, we just did not have this condition. It was just basically all integers. So let me write that one line here. It doesn't really, there shouldn't be any confusion. Right? And it's not a very deep refinement of this lemma. Basically, this thing is just saying that if you pick some a bar for some integer a, then you can just replace a by something in this range, because you could ask, well, what about 0? I mean, it is possible that a is divisible by n, but that's not possible because the GCD of a and n equals 1. Right? In this set, GCD of a and n is 1, so a is not divisible by n, and hence you can always do this. So anyway, if you don't follow what I just said, you can just take this as an exercise to show that Z mod and Z star is equal to that. I don't want to dwell on this too long. And it follows that the size of Z mod and Z star is the number of things between 1 and n which are relatively prime to n, which is denoted by the Euler-Torsion function phi n. This is the Euler-Torsion function which we discussed in a separate lecture. Okay, so with this I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.